Hi guys, this is Sean Alexander with Alexander Tutoring, and today I want to talk about a calculus subject called volumes of revolution. If you're in calculus right now, you're probably doing that right around now. That's something that tends to come up towards the end of the year, and it's quite tricky, especially at first, so I just wanted to help you all out trying to understand these things. So what we have here is two equations, y equals negative x squared plus 1, that's this guy here, and basically a second equation, y equals 0. So what the question is asking, we want to look at the area bound by these two curves. So you can see I've drawn it. The purple line here is the top equation, negative x squared plus 1, and y equals 0, of course, is the red line going across the x-axis. And what this problem wants us to do is rotate. So we want to basically find the volume of this region right here, right? We want to find the volume between that. If we were to rotate this, as you can see here, about the x-axis. So imagine, this is a very visual thing. You really want to imagine rotating this whole object around the x-axis. What volume would it curve out? It'd be some kind of like sphere-ish looking volume, if you can imagine that. Now, here's how we figure out that volume. The trick to all these volumes of revolution problems is you first want to make a differential strip. And so I'm going to make a little strip like this. And the idea is we're going to sum up all these differential strips using an integral. Now, it's a differential strip, so its width is simply dx. That's what makes it differential, right? It's a very skinny little strip that we're looking at here. Well, what's the height of that strip? Well, it's basically the value of the purple function at that value of x, right? So it's basically just the y value. This would have height negative x squared plus 1, right? The equivalent to the y value of the function. That would be the height of our strip. Now, again, this is a very visual, this is great, good problems for visual learners. What I want you to do is imagine your mind, see that strip? Imagine what would happen if we rotated that strip around the x-axis. So if you can imagine that in your mind, if that little strip, it did a 360 around the x-axis, what shape would it carve out? And if you can imagine, it would actually be a disc, right? Like it would carve out a disc whose the face of that disc would be a circle, and the thickness of that disc would be dx. Okay, so what we imagine doing is rotating this little strip around. It makes a circle, and what we're basically doing is add up all those circles across the integral. Okay, so the question is, what is the volume of that disk that is created when you spin this differential strip around the x-axis into and out of the page? Well, basically we can think of the height of this guy, the distance from here to here. That's kind of like the radius of the disk we're looking at, right? And so the top of the disk is a circle. What's the area of a circle? Well, it's pi r squared, right? Then the surface area of that disk, that circular disk, will be pi times the radius. The radius is really the height, right, which we said is simply the value of the y value of the function at that point, pi r squared. Okay, that's the area of the disk. To make it a volume, we have to give it a little bit of thickness, and the thickness of the disk would be dx, right? So now our job is to add up all these, again, if you imagine rotating this thing around the x-axis, we're going to get a disk that comes into and out of the page like this. And basically what our job is to add up all of these disks using an integral as we go from -1 to 1. We're summing all these disks. That's kind of like what an integral does. So we're going to take this disk volume and sum them up from -1 to 1. So that right there, team, is the hardest part of the problem. It's imagining what that disk looks like in your brain. But again, the trick for all these problems is to make that differential strip first and then spin it around, see which shape you get. In this case, the problem's asking for you to spin it around the x-axis. So you spin it, imagine in your mind's eye, spinning that strip around the x-axis. You end up with a disk like this. This is a side view. The disk comes into another page, right? The surface area of the disk is pi r squared. It's a circle, where the radius is this guy, right? Is this equivalent to the height, which is the y value of the top function. Okay, so now we have our integral, so now we just have to solve it. So first step, I can go ahead and pull that pi out of the integral because it's a constant. And then let's go ahead and square out this parentheses here. So I assume you know how to do that, but what we'll end up getting is x to the fourth minus 2x squared plus 1 dx. Okay, and that's a pretty easy integral to solve. Basically, we can split that into 3 integrals, as you probably know. So that's going to look something like minus 1 to 1 x to the fourth dx minus 2 integral negative 1 to 1 x squared dx. I went ahead and took the 2, which is a constant outside the integral, plus integral of negative 1 to 1, just dx, because it's times 1. Okay, so our only job is to solve these basic integrals, which shouldn't be too bad. So we have the pi on the outside here. The first integral, the antiderivative of x to the fourth, is x to the 5 over 5. I assume you know how to do that. Evaluated from negative 1 to 1. Minus 2 times the antiderivative of x squared, which is x cubed over 3, evaluated from negative 1 to 1, plus the antiderivative of dx, which is simply just x, evaluated from negative 1 to 1. Okay? And so now we just plug these numbers in. So when we plug the top limit in here, we get 1 to the fifth is 1 over 5 is 1/5, right? So we get 1/5. And then you subtract the lower bound, so it's minus, and then you plug in the negative 1. Negative 1 to the fifth is, again, negative 1. So we get minus 1/5 or plus 1/5 for the first integral. For the second integral, we get minus 2 times, plug in the 1 to get 1 cubed is 1 over 3 is 1/3. Then we do minus, plug the bottom limit in, negative 1. Negative 1 cubed is negative 1 again, so we get minus is plus 1/3. And finally, for the last one, we plug the top one in to get 1, and then get minus negative 1, or plus 1, for the last integral. Now we just got to add these up, because we're great at fractions. We get pi times 1/5 plus 1/5 is 2/5, minus 2, 1/3 plus 1/3 is plus 2/3, and 1 plus 1 is 2. Okay, so we get equals, go up a little bit, pi, parentheses, 2/5 minus 4/3 plus 2. Get a common denominator, because you love fractions. So here we'll have 6/15 minus 20/15 plus 30/15, getting that common denominator, equals negative 14 over 15. And that is 16 over 15. So we get equals 16 over 15. Pi is the volume you get when this area is rotated about the x-axis. So I really hope that was helpful, team. Again, it's all about drawing that differential strip, rotating around in your mind, figure out what the area that resulting object is, and then figure out the volume, and then doing the integral across the range. Okay, I really hope that was helpful. Good luck. Let me know if you have any questions. Take care.